And just to start by somehow introducing the context for these results, I mean, the real starting point somehow is Schanuel's conjecture in transcendence theory from the 1960s. And then a little bit later, Ax proved functional versions of these conjectures. So that's some results that are known as Ax-Schanuel. So this is due to Ax 1971. Sorry about that. And these are functional transcendence statement for the exponential function, or rather for Cartesian powers of it. And I'll come to the statement of what that is in a little bit. But another kind of offshoot of Schanuel's conjecture is Boris Silber's CIT, which was formulated from thinking about Schanuel's conjecture and model theoretic formulations of that. And this, in turn, led, well, there's a more general version of this called the Zilber-Pink conjecture. And this is Pink's gave the most general version. I should say there were also versions of these conjectures due to Bompieri, Massa, and Zanya, who proved a series of results. But the most general form due to Pink concerns a so-called mixed Shimura variety. So, which I'm going to call X. And I don't want to say too much about this conjecture, this Diophantine conjecture, which somehow combines and it unifies and goes very far beyond things like Model Lang and Andre Oort and a bunch of other, well, it includes conjectures that go very far beyond that, and it's very much open conjecture. Now, these Shimura varieties come with a uniformization map, which I'm going to call Q, which is somehow an analog of this. This actually is a mixed Shimura variety. So these Shimura varieties come with a uniformization by transcendental functions. And our results are essentially what we want to prove are versions of Ax-Schanuel for this Q. But I need to say, I should say that we're going to restrict to the pure case, to the pure Shimura case, not the mixed case. So from now on, unless it's specifically mentioned, X will be pure Shimura variety and its uniformization. And a particular case to think about, maybe the simplest case, is given by the Cartesian product of the J function from the upper half plane to C to the n. So that's maybe the simplest example of this. So in general, this omega, like upper half plane to the n, is some kind of open domain in some complex space. And this map, the J map, is invariant under SL2Z to the n. And in general, there's some arithmetic group that this map is invariant under. All right, so that is, if you like, the setting of what we're trying to do, and the motivation, I guess, the motivation for doing it is to address geometric questions geometric aspects that come up in studying this Zilberpink conjecture. But what it amounts to studying the interactions of algebraic structures in omega versus x. So this omega in general is only a half space, so to speak. It's not a complete complex space like the upper half plane. And so it doesn't really have algebraic subvarieties. But it's open domain in C to the n, so it has algebraic structure. And we'll consider algebraic subvarieties here to be simply components of intersections. So this thing is embedded in some C to the n. It's open there. And we could take, algebraic subvarieties there, and then we intersect them with omega and take components. And there'll be algebraic things that fall off the edge of omega. X, I should have said this right away, X is a variety, it's a quasi-projective variety. And so it's a genuine algebraic variety. And we want to study the interaction of these two algebraic structures. Each of these objects has some idea of what subvarieties are. And we want to study the interaction of those under Q. So a first question that you might ask are, what algebraic, in the sense I just mentioned, V in omega have the property that Q of V is also algebraic? So this Q map is transcendental map, like the exponential function or the J function. So in general, you don't expect the image of something algebraic to be algebraic. But Ax's theorem, which I'm going to state completely, I'm going to state it in a moment, but just to say, it tells us that the answer to this question are exactly translates of Q subspaces. The exponential function takes additive relations to multiplicative ones, so the image of a Q translate of a Q subspace will be a translate of a subtorus. And that's the only algebraic, apart from points in the whole space. Actually, that is and a point anyhow is a translate of a Q subspace. So that is the complete list of algebraic things in omega that are algebraic in the image. And the generalization of this was proved by Ulmo and Yafayev. Let me write. I'll revert to initials in a minute. But the generalization of this is due to Ulmo and Yafayev, that in the general case, the algebraic things whose image is also algebraic, this characterizes the so-called weakly special subvarieties. So these Shimura varieties somehow they're endowed with collections of special subvarieties which are, broadly speaking, subvarieties of X that come with compatible data. And then there's a somehow wider class of weakly special subvarieties that are in some sense translates of those. And that all can be defined sort of arithmetically. I mean, there's a sort of a formalism that gives these, starting off with some semi-simple group, in which it's the arithmetic subgroup, and then you form the domain by modding out by compact and so on. And anyhow, there's a definition of these weakly special subvarieties in that formalism, and they prove that this property characterizes those. They're exactly the things that are algebraic on both sides. And this Zilber-Pink conjecture exactly concerns the interactions of a subvariety of X with the special subvarieties. So that somehow is starting starts to indicate somehow the connection. But the next thing you might ask is, if you take V in omega, something algebraic, when can QV be contained in some algebraic W, proper algebraic subvariety of X? And again, Ax tells you that this only happens when V is contained in a proper. So I'm going to call these weakly specials. Okay, I'm just going to use this terminology, if you like, backwards on the exponential function too. So only when V is contained in a proper weakly special. And if you turn that around, it says that exp of V is Zariski dense in C star to the n unless V is contained in a proper weakly special subvariety. And that's a kind of analog of Lindemann-Weierstrass theorem, which says that if you take algebraic numbers, if you take a tuple of algebraic numbers, then their exponentials are algebraically independent unless those algebraic numbers are linearly dependent over the rationals. So this is exactly the functional statement corresponding to that the exponential of something algebraic is Zariski dense unless it satisfies some rational, it lies in some rational subspace modulo a translate. So this, if you like, this part of Ax-Schanuel, this is the part analogous to Lindemann-Weierstrass or Lindemann's theorem. And this general statement is dubbed Ax-Lindemann, that in general the same thing happens for V in omega. QV is Zariski dense unless V is contained in a proper weakly special subvariety. And this theorem was, or this fact, this property was useful in approaches to the Andre Oort conjecture, part of Zilber-Pink, using a minimal approach. And so this has been established, I guess, well, fully by now in all mixed Shimura varieties, I guess, by my work with Jacob and Klingler, Ulmo and Yafayev, and in the mixed case, Gao. So this property is fully known. So now let's see if I'm not sure hash. All right, so And then the third, the Ax-Schanuel statement, which, anyhow, I'm going to get to. But it's somehow a more general statement. And in one slightly special version of it, you're looking at an algebraic subvariety of V. On the other hand, you have some algebraic subvariety of X, and you take the preimage of that, and then you intersect these, and you want to ask when can the dimension of such an intersection be bigger than you expect. That's one way of putting it. And so, okay, there's a still more general version. This is what you might call the two-sorted version, where you've got a W in X and a V in omega, and there's a more general version where you, and that's the one I'll be talking about, where you simply take an algebraic subvariety in the Cartesian product. All right, so I want to talk just a little bit about the tools that will go into this. Maybe I'll put that over here. So we're going to be using O-minimality. And so the first thing we're going to want is the definability in some O-minimal structure, which is always going to be Rn exp of the uniformizing map restricted to a fundamental domain, to a suitable fundamental domain. So the two pictures to have in mind are the exponential function, where your fundamental domain looks like this, and the J function, where the fundamental domain looks like this. It's the part outside the unit circle between minus a half and a half. This is classical fundamental domain for the action of SL2Z on the complex upper half plane. And in general, the picture somehow looks like that. They're semi-algebraic. There are fundamental domains. The classical ones are semi-algebraic. So the definability is due to, well, Petersils and Starchenko. I'm sorry, what is F? F is a fundamental domain. Oh, okay. Fundamental domain for the action of gamma on omega. And these are sort of the two model pictures. Right, so that definability was established by Petersil and Starchenko. In a particular but very important case. So one of the in a particular but very important special case, and then in general by Klingler, Ulmo, and Yafaev. So once we've got the definability, then you can start using O-minimality. Of course, you can't have this uniformizing map is never definable on the whole space, precisely because it's invariant under an infinite group. And you see that already in the exponential case. So we'll be using the counting theorem of mine with Alex Wilkie, and we'll be playing that off against a geometric volume result due to Huang and Tao. We'll be using some monodromy, the theorem of Deline and Andre. And then we'll be using something with the definable Chow results of Petersil and Starchenko. And so, just to say a couple of things about that. I'll say what the basic example of that result is. We also use some of their other results in that area, the definable remit, and some other theorems in that area. We tend to package it all and call it definable Chow. And we use this theorem somehow repeatedly over and over. And it's sort of a miraculous statement in this context. So just to say that the counting theorem, these other elements were all there in the various previous work on the Ax-Lindemans and in Jacob and my Ax-Schanuel for J and some for the J function. And somehow, as we encountered various obstacles, somehow each new solution was a new use of this result. So this is really a kind of a miracle in this area, and in particular around the differential versions and the differential equations that come up. And in that, just to say that Thomas Scanlon has, I think, even in a more general setting, in studying differential equations of uniformizing maps, has also used these results in similar ways. All right, so maybe now is the time to put the differential Ax-Schanuel on the board. So this is the differential Ax-Schanuel for X. So this is X's. I mean, he gave a number of statements of this result, power series and different forms, but this is the version he gave in a differential field. So K will be a differential field. There'll be a finite number of derivations. There'll be a constant field C. C is simply, of course, that's the kernels of the derivations. So these DIs are derivations on K, so they're additive maps with the Leibniz rule. They commute. They do. Yes. Yes. Right. So the theorem is you take x1 up to xn and y1 up to yn. So these are supposed to be non-zero elements of the field. And they satisfy that dj of yi is yi dj of xi for all I and j. And morally speaking, that says that yi is an exponential of xi. This is you impose the differential equation. And then if x1 up to xn are linearly independent over Q, mod C. And just to say that that condition means that there's no non-trivial sum of Ri xi equals C, where the Ri's are in Q and the C is in C. So that's not all zero. So that's the linear independence of a C is the constant field. Thank you. I'm sorry? Yes, I should have said that too. Yes, characteristic zero. This is Ax's theorem. So C contains, characteristic zero. Characteristic zero. Sorry. And then this is equivalent to the yi's being multiplicatively independent. Mod constants. And then the conclusion is that the transcendence degree over C of the x's and the y's is at least n plus the rank over the k of djxi. That's the statement. And Ax proved this. He gave a couple of proofs, but with differential algebra. This is proved by differential algebra, but he gave another proof with more differential geometry. But our proofs will all use O minimality. Now, so examples of a differential field that looks like this with commuting derivations and characteristic 0 would be some field of meromorphic functions on a disk. So you have a disk with some variables. Open disk in the complex numbers. And then you have meromorphic functions on the disk, and then you have the derivations, which are just partial derivatives with respect to the t's. So that's the standard example of a differential field. And in fact, the Seidenberg embedding theorem tells you essentially that this is the general case, that if you have a differential field, commuting derivations, characteristic 0, finitely generated differential field, you can embed it and isomorphically as a field of meromorphic functions on some disk. So now I want to talk about the complex version, by which I mean the version involving the exponential function. So what I'll do now is I'll take d in c to the n cross c cross to the n to be the graph of this Cartesian product, the exponential function, and I'll take v to be an algebraic subvariety, and I'll take u to be an analytically irreducible component of the intersection. Okay, so this is algebraic, this is non-algebraic. You get some components. Now, on this u, you have the coordinate functions in x1 to the n. And you have their exponentials, if you like, it's functions just on the, so I'll call those the yi's. So we have all those functions on u. And we have derivations, which will just be the derivatives with respect to the xi's. But the number of independent ones you have is only the dimension of u. After that, you get analytic relations, and you don't get any more derivations. And so what Ax tells you in this case is that the dimension of v, so the v is algebraic, so that's telling you the transcendence, that's an upper bound for the transcendence degree over c of all these functions. So it's telling you exactly that this dimension is at least n plus the dimension of u. Right? Because the dimension of u is the rank of the derivations, and n is the number of coordinates, unless U is contained in a proper weakly special subvariety, satisfies a non-trivial, right? So this condition here, that the x's are linearly independent over Q mod C, translates exactly into this, the projection of U onto the C to the n being contained in a translate of a proper Q subspace. So it's exactly, the projection of U is contained in a proper weakly special subvariety. And in this case, because we're actually taking an intersection, we actually get equality here. The dimension can't be, this dimension can't be less than the dimension of V minus n. That's a standard fact about intersections of complex analytic varieties. So Jacob Tsimerman gave a proof of this using O-minimality, point counting, and then it was pointed out, I think, by Martin Bayes, Jonathan Kirby, that this is actually equivalent to the differential version, because if you're given a differential field, you can just embed it, and then it looks like this. You get some component, and you take the Zariski closure of what you get. You take you intersect. You take the component of what you get there, and you do this computation. And that depends crucially, of course, on the fact that all the solutions of this equation are exponential functions. Right. So I want to talk about a basic engine in all these proofs. Is that this U, so in all the proofs I'll talk about, a basic engine is that this U somehow goes through many fundamental domains. You start chasing this U. So there's another domain here, and here, and here, right? There are all these domains. And so you write down a set, maybe I should write it down. You look at the set of, so with any of these Shimura varieties, there's a certain algebraic group that acts as homeomorphisms. So here it's SL to R to the N in the J case. Here it's just translations by reals, and then you've got the integer ones that are sort of giving you the invariance, and here SL to Z. So in the general case, you can always write there's a group G, and you can look at the real points of this, which acts as homeomorphisms of omega, and you act on the variety, and you intersect that with well, I'm going to pretend we're in the two-sorted case. So I'm going to imagine that there's a V in omega and a W in X, and we're studying the interactions of V with Q inverse of W. You can do it either way, but it's easier. You take Q inverse of W, you restrict it to a fundamental domain, and you ask when the dimension of this thing is equal to the dimension of U, which is whatever number it is, and that's a definable set, because this Q inverse of W restricted to F is definable, because Q restricted to F is definable. The actions of V and G, this is purely semi-algebraic. So you write down this set, and then you observe that whenever this U goes through a certain fundamental domain, then there'll be an integer point or a gamma point, in general an SL2Z point or a gamma point, that brings that domain back here. And so you'll see that picture also here because of the invariance. And so this is a definable set that picks up, if you like, an integer point, or this gamma is an arithmetic group. It has some algebraic entries. So you pick up such a point whenever u goes through a fundamental domain. And what you can show, and this is the complex geometry, that this always has to go through many fundamental domains, which means that the number is some positive. This SL2Z, you can put a height just on the size of the entries of the matrix, and you count up how many fundamental domains whose entries are bounded by some height, and you end up with some small positive power of that this thing always goes through. That's complex geometry, and that means that this set has quite a lot of integer points on it, or algebraic points of some bounded degree. And then the counting theorem tells you that there's actually some algebraic family of translates, some positive dimensional family that has this property. And then you look at what happens in that family. So now this, you look at what happens in that family. And if the intersections vary, then you take the union over the family and you make u bigger and v bigger without altering, without increasing the difference between them. But if the u's stay the same and the v's differ, then you take the intersection of the v's and you make the difference between v and u smaller. So you play an inductive game which has to finish with looking at the case where this v is actually invariant under some subgroup. And then you start playing with the subgroup. So this v has stabilizer. So, okay, I want to talk about the modular case. So I'll start with the complex version, and that's very easy. Because I don't have to write anything else. So when you do the modular version, we now look at the j function from h to the n to c to the n. And we take its graph, we take a variety. Okay, I've got more work than I thought to adapt this theorem to the other one, and you take a component. And then the statement is exactly the same, that the dimension of u, the component, is exactly n less than the dimension of v, unless the projection of u, let's say back onto the h to the n, is contained in a weakly special subvariety, which here means, that you have a modular relation that holds identically between two different coordinates, or some j, zk is constant. And you do this by playing exactly this game, but there's a certain complication that I'll allude to a little bit. But I just want to mention that so now, with the complex version, we want to go back and get a differential version. And to do that, you need to impose a differential equation. And to do that, you need to somehow deal with the derivatives. So what happens here is that you take, so this is now the ordinary j. This is j in one variable. Classic theorem of Mahler that j and the first two derivatives and z are algebraically independent over c. But the third derivative satisfies an equation, which is that the Schwarzian derivative of j plus some rational function of j times j prime squared equals 0. And here the Schwarzian is the triple derivative minus 3/2 this thing squared. And this rational function, just to put it out there, is this, 2,654,208 over 2j squared, j minus 1728 squared. That's the differential equation. And so the third derivative, if you rearrange all of this, is rational over q in the first two derivatives, even without the j. And okay, so there's, maybe I won't write down the modular version with derivatives. Well, I'll just write down the differential version. So now we're in this setup again. So now we have some functions, which I'm going to call zi's, ji's, ji primes, ji double primes, and ji triple primes. And they belong to K star, and there are n of them. And the first thing I want to say is that ji prime is really the derivative of ji with respect to zi, because I've got these several derivations around. So what I'm going to write here is that dk of ji is ji prime dk of zi, and that's for all I and k. And then I'm going to do this for the second and third derivative as well, and that'll tell me that this ji is really, it's a function of zi, because not every two functions, not every two elements in a field like this, several derivations, are functions. I mean, the existence of this is not immediate, just given some elements in the field. And finally, I'm going to impose this differential equation, which says that f of ji prime, ji double prime, and ji triple prime is 0 for all I. And then the transcendence degree over C, over the constant field, C, of the zi's and the ji's and the ji primes and the ji double primes is at least 3n plus the rank. This rank of the dizj's you should think of as the dimension of the locus you get when you embed under Seidenberg. That will exactly be the dimension of that locus. And of course there's an unless. And the unless is always the same, and here it's this. That there's some modular polynomials which in two of the j's. So again, the differential version follows from the complex version because you can always do a Seidenberg embedding. When you do a Seidenberg embedding, of course, you get some solutions of these differential equations, but it's a fact to do with the Schwarzian, and I may come to that. Well, anyhow, it's a fact buried in this equation that all the solutions of that equation look like y is j composed with gz for some g in here SL2C. And that's a picture that we'll also want to see. So let me come now to the general case, finally. I'm sorry?
All solutions to which equation are these?
To this equation. But this equation is the same as this one. Yeah. All right, so the general case, so this is finally, so this is plus Mok and plus Jacob. So D is the graph of this Q. V is algebraic. U is a component. And then we have the statement that the dimension of U is exactly n less. So the dimension of X is n, and the dimension of omega is n. So I should have said probably that this is, you see this, D has dimension n, and the ambient has dimension 2n. So this is exactly the dimension count you would expect, that the dimension of U is the dimension of V plus the dimension of D minus the dimension of the ambient. I should have said that. This is the typical dimension count, right? Because this is equal to n minus n minus 2n. The dimension of U is just n less than dim V, unless the projection of U is contained in a proper weakly special subvariety. So that is the first version of this. And I just want to say, I guess, fairly quickly now, that as in the other approaches, you start by trying to move this V around a bit. Well, chasing U through fundamental domains, and you can eventually prove that this V is stabilized by some group. But that turns out to be somehow not helpful. There's some group G, the sort of underlying group of this whole setup, right? And there's the arithmetic group gamma, and you generate some subgroup of G, algebraic subgroup that stabilizes V, but that turns out not to be very helpful. And so here we use an observation of Mok, and just to say that he also could, so it's a certain algebraicity property that I'll say very quickly, and which he could prove using some kind of L2 estimates for D bar, I don't know, some geometry, and which we then translated into Petershill-Starchenko, into definable Chow. But you look at the whole family of, it's easiest to look at this in the two-sorted picture. You've got a W here. You put V in some family. V is an algebraic variety, so you make it you take V in some family, some complete family of varieties, like the Hilbert scheme of all the varieties that look like V, same dimension and degree. And now you go looking in W, and you say, which points of W have the property that when you take a pre-image under Q, that there's some V in this family that goes through that point and intersects the pre-image of W in the same dimension as U. So you go looking for points that look like the setup you have. And that turns out to be an algebraic set. That turns out to be algebraic. And that uses the definable remit. You need to prove something is closed, and then something is definable, and it's clearly invariant. I think that's the point, that's the clue. It's clearly gamma invariant condition. And then what you find is that that set, that algebraic set, it contains the image of U, and so under your assumption, it's not contained in a proper weakly special, and so it has big monodromy. And that's where you get to use the monodromy. Now you look for a V, which is sort of the worst possible. It's invariant under the least possible elements of gamma, but that set is invariant under monodromy, and monodromy is Zariski dense, and so on. And you find out that all of a sudden that this V is invariant under a normal subgroup, a normal Q subgroup. And then the Shimura formalism, I'm going to stop. There's some more, but once this is a normal subgroup, then the whole Shimura formalism takes over and the thing splits. The group G splits up to isogeny, and the domain splits all up to finite algebraic maps, and the whole thing, and then you do an induction, okay, because then V is invariant, if you like. So then the whole thing looks like a cross product in which you've just got the whole variety on one of the products, and you do an induction on the dimension of omega. So I will stop, but having not said that, all studying these differential equations also involves somehow generalizing, studying this Schwarzian for these kind of domains, omega, the Hermitian symmetric domains, the differential equations. And there also you study them in jet spaces, and it's again, it's the theory of the Schwarzians, and it's Petershill-Starchenko definable Chow gives you the differential equations, gives you all the differential conditions. And eventually, so I haven't stated it, but there is a differential version of this as well. Okay, so I'll stop there. Thank you. Thank you very much.